In this video, we're going to talk about capacitors. So what exactly is a capacitor? A capacitor stores electrical charge. It's not the same as a battery. A capacitor uses two metal plates separated by an insulator. And it basically stores charge by taking electrons from one side and pumping it towards the other side. The insulator could be air, it could be paper, it could be water. Anything that doesn't conduct electricity could be the insulator. So that's basically what a capacitor is. It's made of two metal plates separated by an insulator, and it stores electrical charge. Now there are some equations that you need to be familiar with. Q is equal to CV. Q stands for the charge, and the electric charge is measured in the units coulombs. 1 coulomb is equal to 1 amp times 1 second. So Q is equal to IT, where I is the electric current in amps, T is the time in seconds. Now C represents the capacitance, and the capacitance is measured in farads. V is the voltage, measured in volts. So what exactly is capacitance? How can we describe it? I like to think of capacitance in terms of charge efficiency. 1 farad is equal to 1 coulomb per volt. So let's say if we have two capacitors. One has a capacitance of 10 farads, and the other one has a capacitance of 2 farads. Let's call the first one capacitor A, and the second one capacitor B. Now, if we charge up capacitor A to a voltage of, let's say, 1 volt, it can store 10 coulombs of charge. For capacitor B, if we charge it up to 1 volt, it can only store 2 coulombs of charge. Now, what if we increase the voltage? Let's say if we charge up to 2 volts. Capacitor A can hold 20 coulombs of charge. Capacitor B, if we charge it up to 2 volts, if we connect it to a 2-volt battery, it can hold up to 4 coulombs of charge. So as you can see, capacitance is basically charge efficiency. It's how much charge you can hold per volt. As you increase the voltage, you can hold more charge. But if you look at capacitor A, it's more efficient. It can hold 10 coulombs of charge per 1 volt, whereas capacitor B can only hold 2 coulombs of charge per volt. So the higher capacitance means that you can store more charge per volt. Now Q is equal to CV. If you increase the voltage, the charge will increase, as you can see here. However, if you increase the voltage, the capacitance doesn't increase. The capacitance is based on the construction of the capacitor. It doesn't depend on the voltage. To make sure you understand that, the capacitance is constant, and it only depends on the construction of the capacitor. Now, going back to the equation Q equals CV, let's talk about electric charge. You need to understand that electric charge is associated with the quantity of charged particles. And in the case of metals, electrons are basically the charge carriers. They're the ones that are free to move inside a metal. The protons are fixed in place. So the electric charge is equal to the number of electrons times the charge of each electron. Now, the charge of each electron is negative 1.6 times 10 to the negative 19 coulombs. So this charge is discrete. That's the lowest charge that an electron can have. Every electron has that charge. You can't have a charge that's less than this number, unless you have a fraction of an electron. So charge is quantized. Now, you need to know that the unit volt is 1 joule per coulomb. Electric potential, represented by V, is basically the ratio between the electric potential energy and the charge Q. Now, be careful. Electric potential and voltage are not necessarily the same thing, but they're similar. Voltage is the difference in the electric potentials of 2 points. So voltage is delta V. It's the change in electric potential. VB is the electric potential at position B. VA is the electric potential at position A. So electric potential is the electric potential energy per charge. Now, electric potential and voltage, they're both measured in volts. So it's joules per coulomb, which is 1 volt. Voltage is basically the ratio between the work and the charge. It's the amount of work that can be done per unit charge. So work is equal to Q delta V. And I believe there's a negative sign somewhere. Now let's get back to capacitance. We said that the unit of capacitance is the farad. 1 farad is a very, very large number. And only supercapacitors have this much capacitance. Most common capacitors that you may see, like electrolytic capacitors, they might be in the area of a microfarad. It could be 10, 100 microfarads. You have some capacitors that are like nanofarads, and even some in the picofarad level. A microfarad is 1 times 10 to the minus 6 farads. Nano is 10 to the minus 9. Pico is 10 to the minus 12. Now there's another equation that you need to know. C is equal to epsilon sub naught times A divided by D. We said that the capacitance is basically a measure. It's dependent on the construction of the capacitor. So let's draw a capacitor. Here we have 2 metal plates separated by a distance D. Each plate has an area A, and for a rectangle, area is just the length times width. The capacitance depends on the area. If you increase the area, the capacitance of the capacitor will increase because you can store more charge over a larger surface. Now, if you increase the distance, the capacitance will decrease. Given the same amount of charge, if you increase the distance, then the strength of the electric field between the 2 plates will decrease. And therefore, the electric force acted on the charges in between the plates, if there is a charge, will be weaker. And also the capacitance will go down as well. So make sure you understand this. If you increase the area, the capacitance will increase. If you increase the distance, the capacitance will decrease. Now sometimes you can add an insulator. The insulator doesn't have to be air. And if you add an insulator, also known as a dielectric, the equation will change. C will be equal to K times epsilon times A over D. Now let's not forget this little 0 here. So K is the dielectric constant. And for air, K is about 1.0006. It's very small, very close to 1. For a pure vacuum where there's nothing, no gas molecules, K is exactly 1. For other substances, K will increase. For example, let's say if we have quartz. For this material, K is about 4.3. In the case of water, K is about 80. Now, what effect does the dielectric have on the capacitance? As you increase K, the capacitance will increase. So it's very useful to use a dielectric. You can store more charge per volt. C is equal to K times C sub naught. where C sub naught is the original capacitance without a dielectric, and C is the capacitance with the dielectric. So anytime you add a dielectric, the capacitance will go up. However, the voltage will go down. V is equal to the original voltage divided by K. So let's say if you have a capacitor that has 10 farads, and let's say the voltage across it is 20 volts, and the dielectric is 1. Let's say there's air in between it. Now, let's say if we add a material, and the dielectric has a constant of 2. The insulator has a dielectric constant of 2. The capacitance will increase to 20, but the voltage will decrease to 10. So by increasing the dielectric, you will increase the capacitance, but you will decrease the voltage proportionally. But notice that the total charge remains the same. Now, you have to do this when the capacitor is charged but not connected to a battery. Because if you decrease the voltage of a capacitor, and if it's connected to a battery, then charge will flow from the battery to the capacitor, bringing its voltage back up to 20. So you have to charge the capacitor first. Let's say if it's charged to a voltage of 20, then disconnect the battery and the capacitor, and then add the dielectric. When you add the dielectric, when the capacitor is not connected to the battery, the charge of the capacitor will remain the same. The capacitance will increase with the new dielectric, but the voltage will decrease. So Q equals CV. Notice that if we multiply 10 by 20, we're going to get a charge of 200. And that is 200 coulombs. If we multiply 20 by 10, we will still get the same charge of 200 coulombs. So by adding a dielectric to a charged capacitor when it's not connected to a battery, the capacitance will increase and the voltage will decrease. Now, I do want to mention something. The equation that we had, that I drew on a board, that looked like this is the capacitance of a capacitor if a vacuum is used as a dielectric, if there's nothing in between the two metal plates. Now, the equation changes to this if you have a dielectric. It's going to be epsilon times A over D. Epsilon sub naught is the permittivity of free space. It's 8.85 times 10 to the minus 12 coulomb squared per Newton per square meter. So make sure you know that value because you're going to use it a lot. Now, the other epsilon without the 0 is simply the permittivity of the material between the two parallel plates. Now, epsilon is equal to K times epsilon sub naught. So therefore, we have this equation. C is equal to K times epsilon sub naught times A over D. That is, if you replace epsilon with K epsilon sub naught. So this equation is the capacitance of a capacitor if there's nothing in between the two metal plates. If you have a dielectric, then the capacitance can be calculated using that equation. Now let's talk about how to derive the formula for a capacitor. So let's draw the picture of a capacitor. Here are the two metal plates. One of the plates is going to have a positive charge, and the other plate is going to be negatively charged. And so there's going to be an electric field that flows from the positive plate and points towards the negative plate. And these two plates are separated by a distance d. Now you can calculate the electric field if you know the voltage across the capacitor and if you know the distance between the two plates. The electric field is simply the voltage divided by the separation distance. Now the electric field is also equal to the surface charge density sigma divided by epsilon sub naught. And the surface charge density is basically the total charge on that plate divided by the area of the plate. So starting with the equation Q equals CV, our goal is to solve for C. So C is Q divided by V. And rearranging this equation, if we multiply both sides by A, we can see that Q is equal to, that does not look like a Q. Q is equal to the surface charge density sigma times the area. So let's replace Q with sigma times A. Now, using this equation, if we solve for voltage, voltage is equal to the electric field times the separation distance. So it's E times D. Now, using the equation in the middle, if we solve for sigma, sigma, the surface charge density, is equal to the electric field times the permittivity of free space. So let's replace it with that. So E times epsilon sub naught times A divided by E times D is equal to the capacitance. So now we can cancel C. So therefore, the capacitance depends on the area and the separation distance. So that's how you can derive the equation. Now, how does a capacitor work? How does a battery charge a capacitor? Well, let's draw a picture. So let's draw the two metal plates of a capacitor, and let's connect it to a battery. This is the circuit diagram of a battery. The long side of a battery is the positive terminal, the short side is the negative terminal. So this is negative and this side is positive. Now, before you connect the battery, if the capacitor is discharged, it's going to have a voltage of 0. And let's connect it to a 12-volt battery. Once you connect it, there's a difference in potential. Whenever you have a difference in electric potential, the voltage is not 0. Current is going to flow. If the voltage is 0, then no electric current will flow. One way you can think about this is, let's say if you have a level surface, and if you have water on this surface, this water will not flow. The height between position A and position B is the same. However, let's say if you increase the angle, let's say if you put it on an incline, and let's say A is at a higher position than B, then water is going to flow from the high position to the low position. And the more you increase the angle, the greater the velocity. The water is going to flow down with more acceleration, with more force. The same is true with voltage. If the voltage is 0 between 2 points, that is, if the electric potential is 0 between 2 points, no current will flow. Current flows from a high electric potential to a low electric potential, the same way as water flows from a high position to a low position. So while the capacitor have a voltage of 0, current is going to flow in the circuit. Now initially, before we connect the battery at t equals 0, the charge on the two plates is 0. The number of electrons and protons are equal. Now let's say that on the first plate there's about 1,000 electrons, which means that there's 1,000 protons for it to be neutral. In reality, it's probably much more than that. You have like billions and billions of electrons and protons. But let's keep it simple. So we have 1,000 electrons and 1,000 protons. And on the other side, we also have 1,000 electrons and 1,000 protons. Now, in the metal, the protons, they don't move, but the electrons, they're free to move. So keep that in mind. Now, once you attach the battery to the capacitor, which the capacitor has a voltage of 0, because there's a difference in electric potential, current will flow. Now, mind you, current doesn't flow in between the two metal plates of the capacitor because you have an insulator there. And insulators do not conduct electricity. Conductors conduct electricity. So the electrons, they will flow from one side to the other side. Now, because this side has a positive charge, the electrons on the left will flow in that direction, and they will continue to flow on the other side. So basically, what the battery does, using its voltage, which you can think of as an electromotive force, it basically pumps electrons from one side of the capacitor to the other side, and that's how it charges it. So over time, let me draw a new picture. Let's say if 200 electrons travel from one plate to the other plate. Let's see what the situation will be. So if the plate on the left loses 200 electrons, it now has 800. It started with 1,000, but it has 800. Now the number of protons is still the same, it's 1,000. The plate on the right gained 200 electrons, so now it has 1,200. But the protons are still the same. The protons don't move inside a metal. Now if you notice, the left side has a positive charge because it has 200 more protons than electrons, and the right side now has a negative charge. It has 200 more electrons than protons. So the magnitude of the charges on these two plates are equal, but the sign is opposite. So on the left side, the charge is positive Q. There's 200 more protons than electrons. On the right side, the charge is negative Q. There's 200 more electrons than protons. So the charges on these two plates will always be the same. It's just that the magnitude is different. Now over time, the capacitor will be charged to a voltage that's equal to the voltage of the battery. So let's say at 12 volts, it has a charge of 200. Now 200 electrons doesn't correspond to 200 coulombs, but let's just say the charge is 200 just to keep things simple. How much more charge can we store if we double the voltage? If we double the voltage, then we can store 400 units of charge as opposed to 200 units. If we triple the voltage, we can store 600. The capacitance is basically the ratio between how much charge we can store and divided by the voltage level at that point. So if you were to divide 12 by 200, it's going to be equal to 12 over 400. You're going to get the same value. And that value, actually I did it the other way around. It's supposed to be charge over voltage. So if you divide 200 by 12, it's going to be equal to 400 over 24. And that ratio between the amount of charge that can be stored at a given voltage, that's equal to the capacitance of the capacitor. Just keep in mind though, this is not in coulombs. That's just the difference in electrons and protons. In reality, to calculate C, you need to find a charge in coulombs and then divide it by voltage. To do that, it's going to be N times E. So basically, if you have 200 electrons, multiply it by 1.6 times 10 to the negative 19, and then you can get the charge Q. Each electron has this charge. So just to review, a battery charges a capacitor by pumping electrons from one side of the capacitor to the other side. Now, once the capacitor is charged, what's going to happen if we remove the battery and connect it to something that can absorb energy, let's say a light bulb? And let's say the capacitor has enough energy to light up the light bulb. What's going to happen? So let's redraw the picture that we have. So this plate is positive and the other plate is negative. Now both plates still have about 1,000 protons, but the plate on the right has 1,200 electrons and the one on the left is electron deficient. It has 800 electrons. So even though the plate is positively charged on the left, it doesn't mean that it doesn't contain electrons. It simply means that there are more protons than electrons. That's why it's positively charged. And the plate on the right, because it's negatively charged, it doesn't mean that it doesn't have any protons. It simply means that there's more electrons than protons. So when you're dealing with electric charge, think of it as the difference between the number of protons and electrons, because all matter contains protons and electrons. Now, electrons are going to flow from the negatively charged plate towards the positively charged plate. And that's how a capacitor discharges itself. That's how it uses up its energy. Electrons are naturally attracted to protons. So, if one side is negatively charged, the excess electrons will flow towards the side that is electron deficient or that has a positive charge. And as these electrons flow through the wires and through the light bulb is going to light up, provided that this capacitor has enough energy to get the job done. And so that's how a capacitor discharges itself. Now, the capacitor will stop working when the number of electrons are equal on both sides. So once 200 electrons flow through the light bulb, this will now be 1,000, and this will increase by 200, so it's going to be 1,000 now. At that point, the two plates are neutralized. They no longer have a charge. They have equal numbers of protons and electrons, so the charge on both plates is no longer positive Q and negative Q, but rather Q is going to be equal to 0, since the number of electrons are the same and the protons are the same. So once it reaches a state of equilibrium, the capacitor is basically dead. It's discharged. Now, there are some other equations that you need to know before we begin doing some problems, and that is the electric potential energy stored in a capacitor. There's 3 equations that you need to know. The first one is 1/2 QV. It's half of the charge times the voltage. Now we know that Q is equal to CV. So if we replace Q with CV, we can get another equation. The electric potential energy stored in a capacitor is also equal to 1/2 CV squared. So make sure you know these 2 equations, 1/2 QV and 1/2 CV squared. Now there's also another one, because we can replace V with Q divided by C if you rearrange this equation. So instead of replacing Q, let's replace V now. So it's going to be 1/2 times Q times Q over C. So this equals Q squared divided by 2C. So those are the 3 equations that you need to know to calculate the potential energy stored in a capacitor. Now sometimes you may need to calculate the energy density stored in the capacitor. So capital U represents the potential energy. I'm going to write PE. And lowercase u is the energy density. It's basically the potential energy divided by the volume. Not the voltage, but the volume. So how can we derive an equation for this? The electric potential energy is 1/2 CV squared. The volume of, let's say, a rectangle is the length times width times height. The units for volume is cubic meters. The unit for energy is joules. So the energy density is going to be joules per cubic meter. Now C, let's say if we have a capacitor that doesn't have a dielectric, it's going to be epsilon sub naught times A divided by D. And I wrote Q. This is supposed to be squared. So let me go ahead and fix that. That's supposed to be a 2 and not a 3. So what do you think we need to do next? Now we still have a V squared. And length times width is basically the area. We could think of the height as the distance. Now V is basically the electric field times the distance. That is the distance between the 2 plates. So we can replace V squared with ED squared. So we can cancel D, and we can cancel A. So now what we have left over is 1/2 epsilon sub naught E squared. We still have one D value left over, and there's a D on the bottom, so those can be canceled as well. So therefore, the energy density, which is represented by lowercase u, is 1/2 epsilon sub naught times the square of the electric field. So the energy density stored in a capacitor is dependent on the electric field. So just some things to know. Number 1, a metal contains 1.5 times 10 to the 14 excess electrons. What is the charge of this metal in microcoulombs? Well, Q is equal to N times E. So let's find Q. N represents the number of electrons. That's 1.5 times 10 to the 14 excess electrons. And E is the charge per electron. So E is 1.6 times 10 to negative 19 coulombs per electron. So the number of electrons will cancel, and then when you multiply these two values, the units will be in coulombs. So you should get 2.4 times 10 to negative 5 coulombs, and it's negative. Now we want to find the charge in microcoulombs, so let's convert it. 1 microcoulomb is basically 1 times 10 to the minus 6 coulombs. So these units will cancel. And so the final answer is negative 24 microcoulombs. Number 2, a metal sphere contains a charge of 70 microcoulombs. If there are 9.6 times 10 to the 14 protons on this sphere, how many electrons are there? Well, let's convert microcoulombs into the number of protons. Since the charge is positive, this means that there's more protons than electrons. 1 times 10 to the minus 6 coulombs is equal to 1 microcoulomb. And 1 proton has a charge of 1.6 times 10 to the negative 19 coulombs. So notice that the unit microcoulombs will cancel and the unit coulombs will cancel. So you should get 4.375 times 10 to the 14 protons. Now, keep this in mind, this is the amount of excess protons, not the total number of protons. So what this means is that there's 4.375 times 10 to the 14 more protons than electrons. Now, we already have the total number of protons. It's 9.6 times 10 to the 14. If we subtract that number by this number, we can get the number of electrons. So it's 9.6 times 10 to the 14 minus 4.375 times 10 to the 14. And that's going to give us how many electrons are present on this sphere. So the answer is 5.225 times 10 to the 14 electrons. So because we have more protons than electrons, that's why the net charge is positive. But it doesn't mean that there's no electrons. So keep that in mind. Number 3, a tiny dust particle contains 8,500 electrons and 8,470 protons. What is the net charge on this particle? So what should we do in this problem? You need to keep in mind it's the difference between electrons and protons that's important, that's needed to calculate the charge. So here's an equation that you can use. Q is going to equal the difference between the number of protons minus electrons times 1.6 times 10 to the negative 19. So there's 8470 protons and 8500 electrons. If we subtract those two numbers, it's going to give us negative 30. And we want it to be negative because there's more electrons than protons, and so the total charge has to be negative. So the final answer is simply negative 30 times 1.6 times 10 to the negative 19. So the total charge is negative 4.8 times 10 to the negative 18 coulombs. Number 4. How much charge can be stored on a 100 microfarad capacitor when placed across a 12-volt battery? To calculate the charge, Q is equal to CV. The capacitance C is 100 microfarads, so that's 100 times 10 to the minus 6 farads. The voltage across the capacitor is 12 volts. So if we multiply these two, it's going to give us 1.2 times 10 to the minus 3 coulombs. So that's how much charge that can be stored on this capacitor. Now, how much energy is stored in this capacitor? So we can use the equation U, the potential energy, is equal to 1/2 CV squared. C is 100 times 10 to the minus 6, and the voltage is 12. So this is equal to 7.2 times 10 to the minus 3 joules. And that's it. Number 5. A capacitor is connected across a 100-volt power source and has 2.5 joules of energy stored in it. How much electric charge is stored in the capacitor? So make sure you pause the video as you work on these problems. The equation that we need is this one. The electric potential energy is 1/2 Q times V. We have the energy stored. It's 2.5 joules. And we're looking for Q. The voltage is 100. Half of 100 is 50. So 2.5 divided by 50 is 0.05. So this capacitor has 0.05 coulombs of charge stored in it. Now what about part B? What is the capacitance in microfarads? Capacitance is the ratio between the charge and the voltage. So we have 0.05 coulombs divided by 100 volts. So that's equal to 5 times 10 to the minus 4 farads. Now let's convert it to microfarads. 1 microfarad is 1 times 10 to the minus 6. So we got to divide the two numbers. So this is equal to 500 microfarads. Number 6. 100 coulombs of charge is stored when 20 volts is applied across the capacitor. What voltage is required to store 300 coulombs of charge? We know that capacitance depends on the area and the distance between the plates. It doesn't depend on the charge or the voltage, but it is the ratio between the charge and the voltage. So if you change the voltage, let's say if you increase the voltage of the battery, the capacitance will remain the same. Increase in the voltage will affect the charge, but not the capacitance. Q1 over V1 is equal to C. If we change Q and V, let's say Q2 and V2, it would still equal to the same capacitance. Therefore, Q1 over V1 is equal to Q2 over V2. So that's the equation that we're going to use. Now, let's consider part A. The charge increased from 100 coulombs to 300 coulombs. So if we increase the charge by a factor of 3, what effect will it have on the voltage? If Q increases, then V will increase proportionally. So the voltage must increase by a factor of 3. It has to be 60 volts. Using the equation, you're going to get the same answer. Let's say Q1 is 100 coulombs, V1 is 20 volts. Q2 is 300, and we're looking for V2. Let's cross multiply. 100 times V2 is just 100 V2. 20 times 300. 2 times 3 is 6, and then add the 3 zeros. That's going to be 6,000. 6,000 divided by 100 is 60. All you need to do is cancel 2 zeros. So V2 is 60. Now what about part B? How much charge can be stored if 150 volts is applied? Well, let's use the same equation. Let's keep Q1 as 100 coulombs, and V1 is still going to be 20. So V2 is now 150, and let's solve for Q2. So let's cross multiply. So we're going to have 20 Q2 is equal to 100 times 150. And that's about 15,000. So now we got to divide both sides by 20. So 15,000 divided by 20 is 750. So 750 coulombs of charge will be stored if we increase the voltage to 150. So as you increase the voltage across a capacitor, more electric charge can be stored. And the ratio between how much charge you can store at that given voltage can be used to calculate the capacitance. So if you want to find the capacitance, here's what we can do. We can take the Q1 value, which is 100, and divide it by 20. That's going to be 5 coulombs per volt, so that's 5 farads. Or we could take the voltage at 300 coulombs. At 300 coulombs, the voltage is 60. 300 divided by 60 is also 5. So you get the same constant. So we're dealing with a 5 farad capacitor. Number 7. A capacitor is made of 2 square metal plates with side length 3 centimeters separated by a distance of 1 millimeter with air in between the plates. So let's draw a picture. So let's say this is the first square metal plate, and here's the second one. So the side lengths are 3 centimeters by 3 centimeters, and the distance between the two plates is only 1 millimeter. How can we calculate the capacitance? And we have air in between. To find it, we can use this equation. C is equal to epsilon sub naught times A over D. Epsilon sub naught is 8.85 times 10 to the minus 12. The area of the square is length times width. 3 centimeters by 3 centimeters, but you need to convert that to meters. So it's 0.03 meters times 0.03 meters, or you could simply square it. The distance is 1 millimeter, and milli is 10 to the minus 3, so it's 1 times 10 to the negative 3 meters. So you should get 7.965 times 10 to the negative 12 farads. Now a picofarad is 10 to the minus 12 farads. So you can round it and say it's about 8.0 picofarads. Part B. What is the new capacitance if an insulator with a dielectric constant of 4 is added in between the plates? So let's put an insulator in between it. What's going to happen? Anytime you add an insulator, the dielectric constant will increase. The K value will increase. And so C is going to increase proportionally, and the voltage will decrease. So C, the new capacitance, is equal to K times the original capacitance. And K is 4, so it's going to be 4 times 8 picofarads. So now it's going to be 32 picofarads. Now what about the voltage? The voltage is going to decrease, but the equation that you need is this one. V is going to be equal to the original voltage divided by K. The original voltage is 100, and K is 4. So 100 divided by 4, that's a V by the way, is 25. So that's going to be the new voltage, 25 volts. Number 8. A capacitor has 2 parallel plates separated by 2 millimeters and is connected across a 50-volt battery. Part A. What is the electric field between the plates? So if you want to draw a picture, here's what we have. So here are the 2 plates of the capacitor. One side is positive, and the other side is negative. And here's the electric field in between the 2 plates. To calculate the electric field, all you need is the voltage across the capacitor and the separation distance. So it's V over D. The voltage is 50 volts, and the distance has to be in meters. 2 millimeters is basically 2 times 10 to the minus 3 meters. So 50 divided by 0.002 is 25,000. So the electric field is 25,000 volts per meter, or you can use the units in newtons per coulomb. Now what about part B? What is the surface charge density? The surface charge density is the product of the electric field times the permittivity of free space. You've seen this equation earlier in the video. E is equal to sigma divided by epsilon sub naught. So solving for sigma, the surface charge density, it's E times epsilon sub naught. So it's 25,000 times 8.85 times 10 to the minus 12. And this is going to give you 2.21 times 10 to the minus 7 coulombs per square meter. Part C. How much charge is stored on each plate if the area is 0.1 square meters? Well, we know that sigma, the surface charge density, is Q divided by A. Q is the electric charge measured in coulombs. A is the area in square meters. So that's why sigma is coulombs per square meter. So we could find a charge by multiplying the surface charge density by the area. So Q is equal to sigma, which is 2.21 times 10 to the minus 7 coulombs per square meter. And the area is 0.1 square meters. So these units will cancel, giving us the desired unit in coulombs. So 2.21 times 10 to the minus 7 times 0.1 is just going to be 2.21 times 10 to the negative 8. It's going to be smaller. So that's the electric charge stored in this capacitor. Now what about part D? Calculate the capacitance. Let's do it 2 ways. C is equal to Q divided by V. The charge is 2.21 times 10 to the minus 8. The voltage is 50 volts. And so this is going to be 4.42 times 10 to the negative 10 farads. Now let's calculate it using the other equation. So let's use this one. C is equal to epsilon sub naught times A divided by D. So it's 8.85 times 10 to the negative 12. The area is 0.1 square meters, and the distance, 2 millimeters, is 0.002 meters. So this will also give you 4.42. It's really 4.425, but this answer is a rounded answer, times 10 to the negative 10 farads. So using neither equation will give you the same answer. Now let's move on to part E. How much energy is stored in this capacitor? So there's a lot of equations that we can use. So let's go ahead and use this equation. U is equal to Q squared divided by 2C. We've used the other forms, so let's use a different form of the equation. So Q, the electric charge, is 2.21 times 10 to the negative 8 coulombs. That's what we got in part C. Divided by 2 times the capacitance, which is 4.425 times 10 to the negative 10. So this is equal to 5.52 times 10 to the negative 7 joules. Now the last thing that we need to do is calculate the energy density. The energy density, lowercase u, is 1/2 epsilon sub naught times E squared. So it's 1/2 times the permittivity of free space, which is 8.85 times 10 to the minus 12, times the square of the electric field. And the electric field, we found it to be 25,000 volts per meter. So this is equal to 2.77 times 10 to the negative 3, and it's energy per unit volume. So it's joules per cubic meter. And that's it. So that's it for this video. This is just a basic introduction to capacitors. And thanks for watching.